Beneath this frozen Canadian ground lies the richest uranium deposit on Earth. Every worker entering this mine receives a personal radiation dosimeter before going underground. Protective gear at this mine goes far beyond a hard hat and steel-toed boots. The ore body sits more than 1,600 feet below the surface of the Earth. At this depth, the air is pressurized and circulated completely every 20 minutes. Engineers freeze the rock itself to prevent water ground from flooding the ore zone. Each cooling pipe takes up to 8 days to drill and install through solid rock. No worker enters the ore zone. Every extraction machine is operated by remote control. Fragmented rock with uranium concentrations above 15% drops into sealed chambers below. Once at the surface, every batch of ore passes through a radioactivity confirmation scanner. Specialized trucks carry the uranium ore slurry 50 miles to the processing mill. The convoy travels under strict radiological transport protocols across the Saskatchewan wilderness. The Key Lake Mill is where uranium ore is chemically converted into a concentrated powder. The dense ore slurry is discharged directly into large sealed receiving tanks for processing. Crushing reduces the ore to a uniform fine particle size before chemical leaching begins. A rotating ball mill pulverizes the crushed ore into a fine slurry ready for chemical treatment. Sulfuric acid is introduced to selectively dissolve uranium from the surrounding rock minerals. The uranium-bearing liquid is drawn off while waste minerals settle and are removed. Solvent extraction strips the uranium solution of remaining chemical impurities with high precision. Ammonia is added to the purified solution, causing uranium to precipitate as a solid compound. High-speed centrifuges spin away the water, leaving a concentrated uranium cake behind. The uranium cake is heated to 1,560 degrees Fahrenheit, driving off all remaining moisture. The finished uranium oxide is packed into sealed steel drums clearly marked with radioactive hazard warnings. Sealed drums are cataloged and stored in a secured vault before shipment to the conversion facility. Each drum is loaded onto certified transport vehicles for shipment to the uranium conversion plant. At the conversion plant, uranium oxide reacts with fluorine gas to become uranium hexafluoride. Uranium hexafluoride gas is condensed and transferred into certified steel cylinders under pressure. The sealed UF6 cylinders are transported to the enrichment plant where isotope separation begins. Thousands of high-speed centrifuges spin the uranium gas, separating lighter uranium-235 from heavier uranium-238. After passing through the full cascade, uranium-235 concentration reaches between 3 and 5%. The enriched uranium hexafluoride is converted back into uranium dioxide powder for fuel rod production. Organic binders are blended into the uranium dioxide powder to give it the right pressing properties. Several tons of hydraulic pressure compact the uranium dioxide powder into small cylindrical pellets. Pellets are sintered for 24 hours at extreme heat, eliminating internal pores and maximizing density. Each sintered pellet is ground to a precise diameter tolerance of thousandths of an inch. Every pellet passes through a final quality inspection before being approved for fuel rod loading. Zirconium alloy tubing is chosen for its unique ability to allow neutrons to pass through freely. Robotic arms stack 37 pellets precisely inside each zirconium fuel rod tube. Automated welding equipment seals both ends of each tube, forming a complete fuel rod. Each sealed fuel rod undergoes a helium leak test to confirm the hermetic seal is absolutely perfect. 37 individual fuel rods are assembled together into a precise structured fuel bundle. Zirconium brazing bonds the end plates to the fuel rods, completing the structural bundle permanently. Every completed bundle is weighed to verify the precise amount of uranium it contains. Certified fuel bundles are individually wrapped and loaded into specialized shipping containers for delivery. Crates of certified fuel bundles depart the manufacturing plant for delivery to the nuclear power station. The fuel delivery convoy arrives at the nuclear power station under continuous security escort. Station engineers receive and inspect every fuel bundle before it is accepted into the plant inventory. Workers entering the reactor building pass through a full radiation control access system. A remotely operated fuel handling machine loads and removes fuel bundles while the reactor stays online. New fuel bundles are pushed into the reactor channel while spent bundles exit the opposite end. Neutrons collide with uranium-235 atoms, splitting them apart and releasing enormous bursts of energy. Heavy water circulating through the fuel channels absorbs the intense fission heat from the reactor. Inside the steam generators, reactor heat passes through thousands of tubes to boil ordinary water. High-pressure steam enters the turbine hall where it drives turbines in buildings 20 stories tall. Each generator produces more than 750 megawatts of electricity, enough for 500,000 people. A unit transformer steps to generator voltage up to 500,000 volts for long-distance transmission. From the switchyard, 500,000-volt electricity flows outward across the national transmission network. Regional substations reduce the transmission voltage to levels that homes and businesses can safely use. The electricity generated from a single uranium pellet reaches thousands of homes across the region. One uranium pellet the size of a peanut holds the energy equivalent of 1,800 pounds of coal. Nuclear operators monitor the reactor around the clock from a fully instrumented control room. The reactor core sits inside 6-foot-thick reinforced concrete walls designed to contain any radiation release. Two fully independent automatic shutdown systems can stop the reactor in seconds if needed. After roughly a year in the reactor, the fuel assemblies are spent and must be removed from the core. Spent fuel bundles are discharged from the reactor underwater to begin their cooling journey. Spent bundles travel underwater through transfer channels to reach the spent fuel storage bay. Spent bundles must remain submerged in cooling pools 26 feet deep for at least 10 years. The pool's water chemistry is constantly controlled to prevent corrosion of the spent fuel cladding. More than 700,000 spent fuel rods currently rest in cooling pools at facilities around the world. After a decade of pool cooling, spent fuel transfers into dry storage casks for long-term management. Spent nuclear fuel remains radioactive for thousands of years, requiring careful long-term management. Nuclear reactors currently generate roughly 10% of all the electricity produced on Earth. Nuclear energy produces electricity with near-zero carbon emissions during its operational life cycle. Uranium was first identified as a chemical element by German chemist Martin Klaproth in 1789. Manhattan Project scientists used gaseous diffusion first. Modern plants use high-speed centrifuges instead. Power plant uranium is enriched to only 5%, while weapons grade requires enrichment above 90%. Countries like Canada, Kazakhstan, and Australia together account for more than 60% of global uranium production. Every kilowatt-hour of nuclear electricity begins in this frozen ground, in this remote corner of Canada. The uranium ore beneath this ground was deposited by geological forces acting over 1.7 billion years. Not all radiation is the same. Alpha, beta, gamma, and neutron radiation each require different shielding. International Atomic Energy Agency inspectors conduct routine unannounced inspections at every safeguarded nuclear facility. Every gram of enriched uranium produced at a safeguarded facility must meet ASTM international standards and IAEA nuclear fuel specifications. The CANDU reactor uses heavy water as both its coolant and its neutron moderator, a combination found nowhere else. The CANDU reactor is one of the only designs in the world capable of refueling at full power output. A nuclear power station converts approximately 33% of its thermal output into electrical power. Millions of liters of cooling water flow through the station's condensers every hour, returning to the river warmed by only a few degrees. Nuclear stations operate comprehensive environmental monitoring programs measuring air, water, soil, and aquatic life around the clock. Every nuclear station maintains a continuously staffed emergency response organization ready to respond within minutes. Canada is developing a deep geological repository to permanently isolate used nuclear fuel more than 500 meters underground. Each used fuel container is engineered to remain intact for more than 10,000 years in the deep geological repository. Bentonite clay packed around each container swells when wet, sealing the deposition hole permanently with natural material. No other energy source on Earth approaches the energy density of enriched uranium fuel, a fact with profound consequences for climate. A new generation of reactor designs is currently in development, promising smaller footprints, higher efficiency, and passive safety systems. Nuclear operators train on a full-scale simulator that is an exact replica of the main control room. A single nuclear generating station employs approximately 3,000 people in highly specialized technical roles. A nuclear generating station contributes more than $1 billion annually to its regional economy through wages, procurement, and tax revenue. Once built, a nuclear station produces electricity at one of the lowest and most stable costs of any generating technology. Many nuclear stations are undergoing major refurbishment programs to extend their operating licenses by 30 additional years. Nuclear stations provide baseload electricity, constant, uninterrupted power that wind and solar alone cannot reliably supply. From a frozen mine in Saskatchewan to the electrical outlet in your wall, the journey of uranium spans thousands of miles and hundreds of skilled hands. Each pellet in the reactor will generate approximately 45,000 kilowatt-hours of electricity before it is spent. The energy from a single fuel bundle powers a regional hospital for more than a week without interruption. The electricity from nuclear fuel powers classrooms, laboratories, and digital learning tools for millions of students every day. Energy-intensive industries like steel and aluminum smelting depend on the reliable, continuous power that nuclear stations provide. As electric vehicles replace combustion engines, nuclear-generated electricity replaces gasoline with near-zero carbon emissions at the point of generation. While the city sleeps, the reactor continues generating electricity at full power, never pausing, never dimming. As morning demand rises sharply, the station maintains its full output contribution without any additional fuel or startup delay. The spent fuel in cooling pools worldwide contains enough residual energy to power civilization for decades if recycled. A nuclear station licensed for 60 years of operation will prevent the emission of more than 2 billion tons of carbon dioxide. As this reactor operates, new ore is being extracted from the same frozen ground, beginning another fuel cycle. Uranium is element 92 on the periodic table, discovered in 1789 and still powering the world 230 years later. Every second inside an operating reactor, more than 100 billion fission events occur simultaneously, each releasing energy from matter itself. The turbines in this building are spinning at this moment, converting the energy of 100 billion fission events into current flowing to your home. In the modern world, the power needed for modern life comes from anywhere. In a home connected to this grid, a hand reaches for a switch. The chain is complete. One pellet, 45,000 kilowatt-hours. One mine, thousands of hands. One chain reaction, a billion homes. The cooling tower releases only water vapor. No carbon, no sulfur, no particulate. Just water returning to the sky. Beneath this ground, the extraction continues. It has not stopped. It will not stop. From the deepest ground to the brightest light, this is where energy comes from.